Today we are going to study about fuel air cycle and actual cycle. So there are two kinds of cycle, air standard cycle and actual cycle. Okay. So in air standard cycle, working fluid is air and it is taken as a perfect gas and specific heat of air remain constant. Therefore high performance is achieved than in actual performance. In actual gases, other than the monoatomic gases, shows an increase in specific heat with an increase in temperature. Assumptions made in analysis of an actual cycle. First, working fluid is perfect gas throughout the cycle. Second, it follows the combined gas law, which is PV is equal to mRT. Third, the cycle is considered closed with the same air always remaining in the cylinder to repeat the cycle. Physical constant of working fluid is same as that of air, standard atmospheric conditions. Okay. Next, the working fluid does not undergo any chemical reaction. Next, the specific heat of working fluid remains constant throughout the cycle. The compression and expansion process are isentropic process. That means adiabatic process taking place without any friction. Next, the heat is supplied or rejected by bringing a hot body or cold body in contact with the cylinder at an appropriate points during the process. Next topic is fuel air cycle analysis. That means analysis based on actual properties of a working fluid, that is fuel and air mixture. That is also called theoretical cycle or actual cycle. Now we are going to study about assumptions made for fuel air cycles, which are just different from the air standard cycle and which reduces the efficiency of a cycle. There is no chemical change prior to the combustion. Next, air fuel mixture is always in chemical equilibrium. Next, compression and expansion processes are isentropic process. Next, velocity of gases inside the engine cylinder are neglected throughout the cycle. Fuel is completely vaporized and perfectly mixed with air. Burning of fuel takes place at a constant volume in case of petrol engine and at a constant pressure in diesel engine. This was the assumptions made for the fuel air cycles. Now, some notations or note we have to take into consideration. That is, monoatomic gases have only translational energy, whereas polyatomic gases have translational energy, rotational energy and vibrational energy. Okay. Vibrational energy increases with increasing temperature and a specific heat. This is the important criteria that we have to notice, which will be further used in a following cycles or in this chapter. Next topic comes for factors considered for fuel air cycle or factors affecting the fuel air cycle. First factor is actual composition of gases. That means the gases in the cylinder may contain fuel, air, vapor and residual gases. Okay, which will affect the efficiency of a cycle. Or during combustion, the fuel air ratio changes the relative amount of CO and H2. Okay. The next is variation in specific heat. As we have studied that monoatomic gases have only translation energy, whereas polyatomic gases have translation, rotational and vibrational energy. Okay, vibrational energy changes with increase in temperature. So up to 1500 Kelvin it increases instantaneously, but after 1500 Kelvin it increases more rapidly. Next is effect of dissociation. That means that is also called as a reverse process to the combustion. Okay, dissociation means the process of disintegration of combustion product at high temperature. So now we study about a graph given in the figure. So during graph between the percentage mixture and the temperature. Okay, we are considering a cycle with dissociation and without dissociation. So the curve without dissociation gets its maximum temperature at 3000 Kelvin, and the curve with dissociation gets a temperature of 2700 Kelvin. Okay, so there is a reduction in the temperature when it is taken with a dissociation property. Okay, so for SI engine the loss of power takes place due to dissociation. Now next factor is effect of number of moles. So as per the study we can say the number of moles in the cylinder before combustion depend on temperature, pressure and the air fuel ratio. As we know, according to the gas law, PV is equal to MRT. So therefore pressure is directly proportional to number of moles. Now another topic is effect of operating variables on a cycle analysis. There are two operating variables such as compression ratio and air fuel ratio. First is compression ratio. With the increase in the compression ratio, temperature and the pressure at the end of compression is high. Okay. Next is the fuel air cycle efficiency increases with the compression ratio. As the next point is fuel air ratio, and in there are 5 points. That is efficiency, first part. Okay, if the mixture is lean, then the temperature rise is less during combustion, result in low specific heat, thus high efficiency. So there is a graph given between thermal efficiency and the mixture strength. Okay, this is the graph between thermal efficiency and mixture strength. Okay, and this is a lean mixture and a rich mixture, and this is stoichiometric line. Okay, next point is maximum power. In air standard theory, maximum power is achieved at a stoichiometric mixture, and in fuel air theory it is achieved at 10% rich mixture. Okay, and as mixture becomes more richer, the efficiency falls. Now next third point is maximum temperature. Okay, it is achieved at a 6% rich mixture for all compression ratio. And last point is maximum pressure. Okay, pressure during the combustion depends upon the temperature and the number of moles. So there are two more points added to it. Exhaust temperature. Okay, lean mixture means more amount of fuel, more amount of air and less amount of fuel. Okay, means lean mixture gets less exhaust temperature due to less fuel, less combustion takes place. Okay, exhaust temperature is maximum at chemically correct mixture that can be called as a stoichiometric mixture. Next point, mean effective pressure. For all the compression ratio, the mean effective pressure increases with the fuel air ratio. reaches maximum when the mixture is slightly above reach and then decreases. Okay. Now next topic comes here is the difference between actual cycle and fuel air cycle for SI engine. So in actual cycle or operation, following losses occur due to which actual cycle efficiency is much lower than the air standard efficiency. We have 8 points which determines the losses in the actual cycle for SI engine. SI engine means spark ignition engine. First point is time losses. Okay. In theoretical cycle, the burn-in is assumed to be instantaneous, whereas in actual cycle, the burn-in process is completed in finite interval of time. Okay. So the time interval between the spark and complete burn-in of the charge is approximately 40-degree crank rotation. This work lost due to motion of piston during the combustion is known as time losses. Here next point comes is about time losses for spark timing losses and due to incomplete combustion loss. Okay, spark timing losses means a definite time is required to start the combustion of fuel. So the time loss during spark timing and starting of a combustion is known as spark timing loss. Okay, incomplete combustion loss means loss due to incomplete combustion is known as incomplete combustion loss. Okay, direct heat loss is another factor affecting the actual cycle efficiency. Means during compression and expansion process in air standard cycle are assumed to be additivity, but in actual engine this condition is never attained. So when the combustion takes place, the hot energy transfers to the from gases to the combustion valve, and there is loss in the efficiency of the there comes a losses in the efficiency of actual cycle. Next point comes is exhaust blowdown loss. In this, it is assumed in ideal cycle that the valve opens and closes at a dead center, but in actual practice the valve opens at some angle of crank before the piston reaches the TDC or BDC. So the loss during this exhaust is known as exhaust blowdown loss. Next is pumping losses. Pumping loss. In ideal cycle, it is assumed that the air is admitted into the cylinder at atmospheric pressure, but in actual practice it is not possible to transfer the air to the cylinder at atmospheric pressure. So for that there is need to be a pressure difference. So the losses due to pressure difference are known as pumping losses. And next point comes here is the rubbing friction loss. Okay, this rubbing friction loss is the loss due to the rubbing or friction between the piston and cylinder walls, friction in various bearings, and also the energy spent in operating auxiliary equipment such as cooling water pump, ignition system, fan, etc. Okay. The next point is losses due to incomplete combustion. The next point comes here is dissociation losses. Losses due to dissociation or disintegration of a element of a working fluid. Okay. The next loss is due to the variation of specific heat. Okay. Now next topic comes difference between the actual cycle and the fuel air cycle for the combustion ignition engine, compression ignition engine, sorry. In these engines, losses are less than petrol engine. The main loss due to incomplete combustion of fuel.